Welcome to lecture 41 of our course on high performance computing. This is the last lecture in this course. In the previous lecture we had learned a lot about the different functions of the MPI message passing library, which is what a lot of people use to write their parallel programs to run on parallel architectures or clusters of workstations, using message passing as the mechanism for communication and interaction between processes. We had looked at the different versions of send and receive which are used for communication in MPI, some of the underlying very important concepts such as the communicator and the rank, etc. We were looking at an example of one particular kind of group communication which is provided by MPI. Group communication is the idea that since there are frequently situations where we want one process to communicate with a group of processes, where it might not be that efficient for the programmer to talk about individual sends and receives between one process and let's say 100 other processes, MPI fortunately provides us with a single function which can be used for a process to communicate with a group of processes, and there could be 100 or 1000 processes within that group. One such example is the gather group communication function, through which data can be collected from each of the individual processes from the parallel program into one of them, and that is why it is known as a gather. So in this particular example, which I just go through once again, we have a situation where there are some number of processes which are part of the parallel program. Now any MPI program will be run so that the same program, the same executable will be running as for each of the processes on each of the processors. Therefore, it is typically the case that each of the processes will check to find out what its own identity is. And in the subsequent parts of the program will be written so that based on which process you are talking about, it will do either one thing or another. So in this particular example, after all the processes have determined who they are in terms of what their rank is, one particular process which has a rank of 0 actually finds out what the size of the communicator is. In other words, it tries to find out how many processes, in some sense, this program is running as. So if the program is running as 100 processes, then it will set its variable group size to 100. Right? And what is subsequently going to be done is it allocates a buffer. So the process called 0 allocates a buffer within its virtual address space using malloc of adequate size to allow for each of the 100 processes involved in that communicator to send it 10 integers. So in fact the size of this buffer in this particular example is going to be 100 multiplied by 10 multiplied by 4 bytes. So that's the size of the buffer. You'll note that each of the processes in the communication is going to send 10 integers corresponding to the 10 elements of its variable data. Data is declared in each of the processes as an array of size 10. So 10 multiplied by the 10 integers multiplied by the 100 processes who are going to be involved in the gather. So once the buffer has been allocated, the root process along with all the other processes, so note that what follows is going to be executed by all the processes in the parallel program, to all of them execute MPI gather, in which they specify that the data in their local variable called data, which includes 10 integers, is supposed to be gathered into a buffer leading to and the size of the buffer is group size multiplied by 10 integers, which is present in process with rank 0 of the MPI communicator world. So in this way it is possible for even more than one piece of data, more than one integer, to be communicated using the same functions that we had talked about. Okay, now let's proceed to look at a specific example of a parallel computation. The specific example which I am going to look at is we're going to try to write or at least understand the structure of an MPI program which is going to do a calculation, and the calculation which I am going to refer to is actually to calculate the value of the constant pi. What I mean by pi is pi, which you know has a value of 3.141592565 whatever. But the purpose of this program is to try to calculate the value of pi more accurately. It's going to use some kind of a numerical integration procedure. We're not too concerned about the actual procedure, the computation that it's going to do. We're more concerned about the fact that it's going to be executed as a parallel program. So the work of computing pi is going to be divided among a larger number of processes, each of which will do some of the work towards computing pi. Then all the data from all of them will be accumulated to actually get the final value of pi. And we want to understand more about how this could be done with a single MPI program. So we are going to set this out by writing the MPI code. I am going to show you the MPI code. We are not going to reason about how the calculation is done. Just I want you to just bear in mind that we are going to be using some kind of a numerical integration technique. So we are going to be computing the area under one quadrant of a circle, and that quadrant of the circle is actually going to be divided into multiple slices. Each of the processes will compute one of the slices of area. Possibly, if the number of processes is low, each of the processes might compute more than one slice, accumulate that area and send it back to the root process, which will do the accumulation and therefore the computation of pi. So that's the nature of the computation, and the actual statements in C which do that integration are not too important to us. They are included in some form, but please don't pay too much attention to them. Now, as in any MPI program of the kind that we are talking about, where we are assuming that it's written in an SPMD mode, the same executable is going to be run on each of the processors as a separate process. Therefore, it will be the case that each process will have to determine the size of the communicator as well as its own rank, and we know how to do that now. So the program starts with MPI init, and each process subsequently will find out how many processes this program is running as and what its own identity is. So the one process will receive a return value of, if the program is running as 100 processes, each of them will end up with knowledge that there are 100 processes, and of the 100 processes, one of them will receive a value of MID equal to 0, another will receive a value of MID equal to 1, and so on. One of them will receive a value of MID equal to 99. So each of them will have a clear understanding of its distinct rank. Subsequently, one of the processes, which I am designating as the master process, will take some input from the user. Now you should bear in mind that parallel programs, like the ordinary programs that we write to run on single computers, may have to interact with the user, and therefore there may be some calls to get, for example, additional information from the user. In this example, we are going to get feedback from the user about how many slices we have to do the integration over. So basically what happens is the process known as P0 is the only one which will find my ID equal to 0, and it will print a message on the console of the parallel computer asking the user to type the number of intervals that he or she wants to be used in the computation. This will then be read into a variable called n. Now the variable called n is a local variable in some sense of process P0. Remember that the other processes will not know the value of n. Therefore, if process P0 wants the value of n to be known across all the processes in the computer, in the parallel program, then it would have to broadcast the value of n to all the processes comprising the parallel program, which is what it does next. It will broadcast the value of n to all the processes which constitute this parallel program, and it can do this using the MPI broadcast group function. So it mentions that, again, somewhere in here there should have been a declaration of a variable called n. So each of the processes has a variable called n. It just happens that the copy of n in the address space of process P0 will have the value that is meant to be broadcast. For example, if the user had typed in that he wants 1024 intervals to be used, then the value of n in the address space of process P0 will be 1024. Of course, the value of n in the address space of other processes will have whatever its default value is, possibly 0. But after the broadcast, which is done by process P0 as root, using the value in its variable n, which is one integer value, to all the processes in communication world. So after this statement, after this function has been executed by all the processes which comprise my parallel program, the value of n on all the processes will be equal to 1024. That is what the broadcast function achieves. Subsequently, we can go into the region of the program where each of the processes does its step of integration or its steps of integration. And the number of steps that each process will have to do will depend on how many intervals the user specified, as well as the number of processes that this program is running as. Remember that this same parallel program could be run as 2 processes, or as 4 processes, or as 16 processes. The number of processes is not hardwired into the program. When I run this program using MPI run, I have the option of specifying how many processes I want it to run as, and I could at that time decide to run it. This is in response to the command prompt. I could decide to run it as 16 or 32 or 64 processes. Now subsequently the user specifies that he wants the program to calculate the value of pi using 1024 intervals. In other words, dividing the area of the unit circle quadrant between 0 and 1 in 2024 intervals in doing the numerical integration, then clearly if I have 16 processes doing this work, then each of them should do more than one of the intervals. Therefore, within the region of the program that is going to do the work, I am not including the master process, I am using all the other processes. So that is why I will refer to the other processes as the slave processes, and each of them will do its work in the numerical integration. So the way that this is being done is that it calculates the size of, again remember we are doing this calculation by quadrature, the unit circle, and calculating the area under this. So it finds out the slice size, in other words 1 divided by the value of n, that is the actual width of this region which is going to be, whose area is going to be calculated. It initiates a sum which is the total area that it has computed in the slices that it deals with to 0. Subsequently it does some number of slices depending on what its ID is. So if its ID is 1, then it computes the second and some subsequent number of slices until it has computed slices reaching the end. So basically the different processes are picking consecutive slices. The process number 1 will do, as seen over here, slice number 2, process number 3 will do slice number 4, and so on. And then after the last process has done its work, process number 1 will do the next slice, and so on. That is what is being achieved by this integration. So the step of integration I am not going to refer to, but after we have reached this point in the program, each of the processes has done its calculation of its region of this quadrant of the unit circle. It can then calculate what its contribution to the value of pi is, and now all the processes can communicate what they think their contribution to the value of pi is back to the root process using MPI reduce. In MPI reduce, the nature of the computation is each of the processes is going to communicate its value of pi to the root process, and what it's going to communicate is one double precision value, because the computation that we talked about was clearly not computing an integer value but a double precision value. The reduction is going to happen by adding all these values together and putting them into the variable called pi inside process P0. The communication includes all the processes inside MPI COM world. Subsequently, process P0 can be written so that it prints out the value of Pi. In effect, what we have achieved is, and then the finalizing can be done. What have we achieved? We have achieved a clear understanding of how we could write a parallel program which is actually computing the value of pi, dividing the work of the computation across some arbitrary number of slave processes. And we have in some sense, we have not understood the mechanics behind how the computation of pi is done. I will leave that as an exercise for you. But very clearly, more complicated or even simpler parallel programs are well within the purview of what can be done using a small number of MPI communication primitives. Okay, now with this understanding of MPI, and we have demystified MPI, we understand that it's not too difficult to move from writing C programs to writing parallel programs which can run using MPI, parallel programs that can run on large clusters of workstations or large parallel machines, thereby reducing the amount of time that it would take to execute let's say a program that may have initially taken a huge amount of time on a single computer. Now with this, we'll move into a slightly more abstract mode. I won't talk about MPI anymore, but I'll talk in general about the activity of parallelizing a program or writing a parallel application. In terms of, we'll run through a few examples of the kinds of decisions one may have to make along the way and so on. Now, the perspective that we're going to take on this is that we have a sequential program or algorithm, and we're interested in understanding what has to be done to move from that sequential program or algorithm to a parallel version of the algorithm, of a parallel program to achieve the same objective in a shorter amount of time, since we have a parallel computer. Now, the general idea is, by saying that we have a sequential algorithm, all that I mean is we have some understanding of how we would do or how we would solve the problem or achieve the objective if we had only one computer to achieve the objective on. So that's all that I mean by saying given a sequential program or a sequential algorithm. We are more concerned about, given a specification of a problem, and we may have the specification of the problem by an understanding of how to solve it for a sequential computer, how do we go about producing a parallel program to achieve the same objective? people will often talk about a 4-step procedure for writing a parallel program, and they may talk about the 4 steps, naming them as decomposition, assignment, orchestration, and mapping. And let me just give you a rough idea of what these steps are, just for completeness. Now, the objective of decomposition is to identify the parallel tasks which could be used as the parallel processes inside the parallel program, but essentially identifying the way in which we are going to break up the work in order to get the maximum possible parallel activity. Now, just note that if in writing a parallel program, it's quite easy to say, let's suppose I wanted to write a parallel program to compute the value of pi, as we just did. It's quite easy to say, okay, I'll write a parallel program which runs as 2 processes. But as we saw in the previous example, it is quite easy to write a parallel program which runs as 16 or 32 or 64 or some arbitrary number of processes to compute the value of pi. In general, depending on what the application is, there may be an appropriate number of parallel tasks that will be best for achieving the parallel objective, and that identifying what those parallel tasks might be in the step called decomposition may be the first activity to take place. Rather than trying to think right from the beginning about the variables or the nature of the reducers and scatters, etc., at the first step, try to figure out what is the nature of the parallelism and what might be the appropriate level of parallel task activity. This is also important for us from the perspective of what we have seen in the previous lecture about Amdahl's law, which told us that essentially the speed up or the extent to which parallelizing a program might cause it to be speeded up is going to depend on the fraction of the sequential version of the program which could not be parallelized at all. And this initial step will give us some idea about what that sequential fraction might be. Now, after we have got some perspective on how we would like to decompose the problem, the next step is to actually do assignment, which is grouping the tasks into processes. Now, in the first step, we had explicitly not talked about processes, but rather about tasks. And once again, the right way to think about this is, once again, to think about our pi calculating program. If you look back or think about the pi calculating program, each of the processes was not computing one slice of the numerical integration task, but rather many slices of the numerical integration task. In thinking about the decomposition of the problem, I might in fact not have thought about the processes at all, but I may have thought about the individual tasks. I may have thought, okay, we can actually have 1000 tasks, 1024 tasks which could be done. Now, subsequently, when I think about the number of processes that might make sense for the application, I might realize that having 1024 processes may increase the overheads of running this as a parallel program, because the size of the gathers, the size of the broadcasts will become a little bit more, and we know that underlying any one of those group communication primitives, there are going to be a large number of sends and receives, and therefore the fewer the tasks, the more efficiently those are going to take place. So taking this into account, we may actually come up with a situation where we started off with the 1024 tasks as the decomposition of the pi calculating program, but we broke it down into a smaller number of processes, because we realized that this may actually lead us with a better balancing of load across a number of processes in terms of the distribution of communication work among the processors of a parallel computer system. Now, once we have this picture of the parallel program in terms of a collection of processes, we can then do what is called orchestration, trying to reason about at what points in time, at what points in their calculation will the processes have to be synchronized, or at what points in their computation will the processes have to communicate with each other. And from this we can estimate what the overheads or the costs associated with the synchronization or the communication among the different parallel processes is going to be. And in coming up with this idea of what the overheads are going to be, we can make the effort of trying to reduce the overheads of those communication. For example, if at some point we had been thinking about using point-to-point communication for a particular variable, and we realize that the communication is happening across all the processes, we may see that we could reduce the cost by using group communication. But there may be other ideas that could come to mind in the step of orchestration. So in orchestration, we move from a picture of what the processes are to how best to communicate, to set up the communication between the processes. In the last step of parallelizing a program, people sometimes talk about mapping. And this is the step of the parallel programming where we actually relate the processes to the individual processors of the computer system. So mapping refers to the mapping of processes to processors. And this is not something that we talked about having explicit control in terms of our MPI program. You'll recall that when we talked about the MPI program, the base assumption was the same program is run on all the processes, and we don't know how many processes the program is going to run on. But in talking about causing the program to execute, we do have the capabilities of specifying exactly which and how many processors are going to be involved in the execution of the program. And there may be other situations for other kinds of parallel programming scenarios where we actually have control over which processes are going to run on which processors. This is not immediately available to us in MPI in the form that is referred to over here, and might not therefore be a typical step in writing an MPI program. Okay, now with this very general introduction, these are the terms that you will see if you read books or tutorials on parallelizing a program. I wanted to look at one or two specific examples in which I specify a task, an activity, and then we'll think about various possibilities about how it could be parallelized. Okay, now the first activity I'm going to talk about is what is known as implementing a barrier. We had come across the term barrier when we talked about concurrent programming. I introduced the barrier as being a kind of a synchronization primitive. We had also come across the barrier when we looked at the list of MPI group communication primitives, because the barrier is one of the MPI group communication primitives which we did not look at. I talked only about, I believe, gather, scatter, reduce, and broadcast. But one of the group communication primitives functions in the list that I put before you was in fact the barrier. So ultimately the barrier is the name of a well-defined synchronization primitive. And let me just tell you what a barrier is. It is a process synchronization primitive. It could be used in concurrent programming. It could be used in parallel programming. And the general idea is, if I have a situation where there are n cooperating processes and each of them includes a call to the barrier primitive, in other words, there are n processes, process P0, process P1 through process Pn minus 1, and each of them calls the barrier function or the barrier primitive, then each process entering the barrier, in other words, each process which reaches call to barrier, gets blocked on the barrier call until all the n processes have reached the barrier call. In other words, it's possible that process P0 reaches the barrier function call first, but it will not proceed beyond the barrier function until all the n processes have reached the barrier function in their parallel programs, which means that the barrier function call inside the parallel program constitutes some kind of a line beyond which no process can proceed until all the processes have reached the barrier. And that's why the name barrier seems to be a fairly good name for this function. It can be used to synchronize all the processes which are participating in the barrier. You should note that I could write a parallel program which has one additional process which is not participating in the barrier. Right? So one could think about using a barrier to synchronize some number or some subset of the processes. The subset could include all the processes, or it could be less than that, depending on the needs of the parallel program. So it seems likely that the barrier synchronization idea is going to be quite useful in writing parallel programs, which is why it is included as a basic group communication primitive in MPI. Now, why do I talk about implementing a barrier as an appropriate example through which to understand something about parallelizing applications? As we think about the idea of implementing a barrier, we could come across various ways in which the barrier function, we're not talking about how you would implement the barrier function, we could think of various ways that the barrier function could be implemented. This is along the lines of how we talked about the lock primitive. We looked at a few possible ways to implement lock, acquire lock and release lock. Some of our ideas were wrong, but we ultimately came up with ideas of how the lock, acquire lock and release lock functions could be implemented. We want to go through the same exercise for the barrier function. Okay, so the net effect of using a barrier is that the n processes which are synchronizing on a barrier will all depart from the barrier function call synchronized. None of them would have done anything other than having just come through the barrier. So each of them would have done all of their work up to the point of the barrier and no more at the point that they proceed beyond the barrier. Okay, now one simple idea for how we could implement a barrier. Remember, the barrier involves n processes. Each of the n processes is ultimately going to call the barrier function, and we know that each of them will proceed beyond the barrier only after all of them have reached the barrier. Now, one simple idea about how we could implement the barrier could be that we could use a shared variable to implement the barrier. And if the system that you're working on has shared variables, then very clearly a shared variable could be used to implement the barrier. Remember that we used a shared variable to implement a lock, and a lock is a basic synchronization mutual exclusion primitive. There was nothing wrong in assuming that you have shared variables in talking about an implementation. So how could I use a shared variable to implement a barrier? The simple idea is something like this. I'll have a shared variable which is going to be used as a counter. I'll initialize the shared variable to 0. Subsequently, when any one of the processes reaches the barrier function, what will happen inside the barrier function, in other words the body of the barrier function, will be to increment the counter variable and then to wait until the value of the counter variable becomes equal to n. So within the barrier function I am going to find something like counter plus plus and busy waiting on until counter becomes equal to n, right. So while counter not equal to n, busy wait. So that is what I expect could be present inside the barrier function, right. That is one possible implementation of the barrier function, and you could note that it will work, because if initially the value of counter is 0, after process P0 reaches the barrier, it will make barrier equal to 1, but it will continue to busy wait on the loop because barrier has not yet become equal to n. You can assume that n is equal to 100, so n minus 1 is equal to 99. Subsequently, one of the other processes reaches the barrier, increments n to 2. It also finds that the counter is not equal to n, 100, and therefore it also busy waits on its loop within the barrier function. And this keeps on going until the last of the n processes increments the barrier to 100, at which point in time all of the processes will find out that n has become equal to 100 and they will exit from the busy wait loop. And therefore this is a perfectly legitimate way to implement a barrier if you have a shared variable system. Now the question that arises now is, what if I have a system in which there are no shared variables and I have to implement the barrier using message passing? Now that is the situation that we want to think about. How would you implement a shared variable using message passing? And you will now realize why this is an interesting and an important example, because what we are going to talk about now is the various ways that the MPI barrier function could conceivably have been implemented. You will note that the MPI barrier function is available in MPI, but is ultimately written as a function within the MPI library and is possibly written using MPI send and receive function calls, the more primitive kind of message communication primitives provided and supported by MPI. And if there are many different ways of doing that, then very clearly we would want to make sure that MPI barrier uses the best possible way to implement the barrier, which is why looking at a few alternatives in terms of decomposition, orchestration, etc. might be useful for us to understand more about parallel programming in general. So it's a simple example, but a fruitful one, because we will be able to understand a little bit more about how important it is for the people who write functions like MPI barrier to think through the problem a little bit. Okay, now I'm going to start by starting with a very simple idea of what is typically known as a linear barrier. We're going to write pseudocode for it. We're not going to write actual C functions or MPI functions. We're going to use a pseudo notation to save some time. Right, so the situation is that I'm going to create the barrier between processes P1 through P7 using process P0 as some kind of a master process. So process P0 is not one of the processes participating in the barrier, but is used as a master process to create a barrier that can be across process P1 through P7. So the way that we'll start off by looking at the functioning of the barrier implementation pictorially. The way that the linear barrier is going to work is that when each of the processes reaches its barrier, the call to the barrier function within its program, it sends a message to the master process. So when a process reaches the barrier call within its own body of within its own program, what's happening inside the call to barrier is, first the process sends a message to the master process. So the first process that reaches the barrier sends a message to the master process, then the second, then the third, etc. So at some point in time, all the 7 processes would have reached the barrier and send a message to the master process. What should be happening within the master process? Within the master process, when it receives a message from any one of the n processes, in this case n is equal to 7 processes participating in the barrier, when it has received a message from each of the n processes participating in the barrier, it proceeds to send a message to each of those processes in return. So what is happening inside the master is it is keeping track of the messages that it has received, and as soon as it has received a message from each of the n processes, it sends a message in return to each of the n processes, in this case 7. So it sends in order to process P1 through P7. and as soon as the process P1 through P7, each of them receives a message from the master, it knows that it has finished with the barrier and can proceed to out of the barrier. Now, this is how the linear barrier works. You can understand why it's called a linear barrier. It's called a linear barrier because in each of the steps that we talked about, each of the processes, in the first step, each of the processes sends a message to the master, and in the second step, the master sends a message to each of the 7 processes. And each of these is happening in some sense in a sequential order, as we will see when we look at the pseudocode. Now, what we mean by pseudocode is we're actually going to look at the statements, the C-like or MPI-like statements that are going to be executed by the master and by the slave. So the sequence of events is, we said, as soon as each of the slaves reaches the barrier, it will do a send to the master. So if I looked into the barrier function, this is what I would see in the slave. When it enters the barrier, it does a send to the master. What does the master do? The master is waiting to receive a message from each of the slaves. Therefore, within the master, we expect that as part of the implementation of the barrier, there's going to be a for loop, which is going to be executed in our example 7 times, and each time through the for loop, it's going to receive from any of the slaves. It doesn't matter which of the slaves it receives from. The important thing is that it executes receive 7 times, and that each time through the loop, it's going to receive from one of the slaves. So it could be the process P3 reaches the barrier first, in which case it sends a message to the master, and the master receives the message right away. And we know that this is possible using the MPI primitives, primitive send and receives, by having a receive from any source kind of a call. Now, after the master exits from this loop, we know that it has received a message from each of the participating processes in the barrier. It can then go ahead to a second loop where it sends a message to each of the processes participating in the barrier. So it sends first to process P0, then to P1, then to P2, first to process P1, so this should be corrected to 1. It doesn't send to, in our example, the process is not participating in the barrier itself. So this should be also corrected to 1. So each of these loops is executing n-1 times, where n-1 is what is equal to 7. Okay, so then the master process sends a message to each of the slave processes. What happens in the slave? The slave just receives a message from the master. Therefore, what we're looking at down here is the implementation of the barrier function as far as each of the slaves is concerned. This is what the slave is going to execute. The slave executes, when it reaches the barrier, it sends to the master, and then it receives from the master. And as soon as both of these calls have finished, it is done with the barrier and proceeds to the next part of its program, and it is synchronized with the other processes synchronizing on the barrier. Why is it called a linear barrier? You'll notice that the amount of time that it takes for this barrier to work is going to be determined by looking at the master. The master first has to go through the upper loop 7 times, or n-1 times in general. Then it has to go through the lower loop, again 7 times, or n-1 times in general. And therefore, this is a procedure in which it is linearly or sequentially going through each of the child processes, receiving from one of them each time through the first loop, and sending to one of them each time through the second loop, which is why it's called a linear barrier. And you should notice that we could quite easily encode this in MPI by just replacing receive by the appropriate MPI receive, etc. Quite easy to map this pseudocode. I call it pseudocode because I have not actually used MPI sends and receives here, but I'm using a more general version, just like pseudocode in C. So we understand how this linear implementation of the barrier could work, and further we understand that it should be easy to do better than this. Let me give you a simple idea. Let's suppose that in this version of the barrier, I'm trying to synchronize all the 8 processes from P0 through P7 with each other. And the idea which I'm now going to do is, I'll avoid making the master explicitly I'll avoid having the process P0 as the explicit master as far as all the processes are concerned, by distributing the communication that each process will do when it reaches the barrier. So what we're going to see from this point on is the kind of messages that each of the processes will send when it reaches the barrier. So you'll notice that what happens when process P1 reaches the barrier is that process P1 sends a message to process P0. When process P3 reaches the barrier, it sends a message to process P2, and so on. So we're talking about 4 messages that are sent when process P0, P3, P5 and P7 reach the barrier. What does process P0 do when it reaches the barrier? It does a receive for a message from process P1. What does process P2 do when it reaches the barrier? It does a receive of a message from process P3. Therefore, what we are seeing in this first line of 4 message sends and 4 message receives is that process P0 and P1 have both reached the barrier by the time the send and the receive have completed. The same is true as far as P2, P3, P4, P5 and P6, P7 are concerned. Now, in the second step, we have not yet finished with our implementation of the barrier, but in the second step of implementing the barrier, we will try to synchronize or spread the information about which processes have reached the barrier by causing process P2, once it has come out of the receive of the message from P3, to send a message to process P0. What is this going to achieve? This is going to achieve the equivalent of process P0. After having reached this point, it then does a receive on a message from process P2. So by the time process P2 has finished with the send receive interaction with process P2, it is known that P0, P1, P2 and P3 have all reached the barrier, and a similar situation would have been received as far as P4 through P7 are concerned. Now, with one more communication, it's going to be possible for process P0 to become aware of the fact that all the processes have reached the barrier, and that message will have to be sent from P4 and received by P0. So with a total of 4 plus 2 plus 1, or 7 message sends and 7 message receives, we have been able to inform process P0 that all the processes have reached the barrier. Subsequently, all the processes have to in turn be informed that this information Therefore, there will have to be another round of communication in which process P0 first informs process P4, and then process P0 informs process P2, and process P4 informs process P6. In effect, the reverse of what happened in the first round of communication. But soon all the processes will have received the information that had been accumulated into process P0 at this point in time. Now, if you look at this, you may see that the number of messages that had to be sent has not really come down from what had to be done in the case of the linear barrier. But what has been achieved is that it is no longer necessary for process P0 to receive a message from each of the other processes in a linear fashion. And the initial communication between P0 and P1 could happen in parallel with the initial communication between P2 and P3, which in turn could happen in parallel between the other initial communications, therefore allowing the parallel nature of the parallel machine to be exploited, causing a reduction in the total amount of time that it takes to actually achieve the barrier synchronization. So we may not have reduced the number of messages that have to be communicated. We still have 7 messages to be communicated in the upper half and 7 messages to be communicated in the lower half, but the amount of time for the message communications to happen has been cut down because of the parallelism that is exploited. Now, when you look at this diagram, or when you look at half of this diagram, you could immediately come up with a name for this kind of implementation of a barrier, because what we see over here is something that looks very much like the tree that we talked about not too long ago, and this implementation of the barrier is often known as a tree barrier. This also leads us into some possible improvements of the idea of the barrier implementation beyond this. For example, we could imagine that we could more aggressively overlap the way that the communication is happening. Conceivably, within the first round, rather than process P0 and P1, process P1 sending a message to process P0 and process P0 just sending a message to process P1 in the second half of the communication, you notice that process P0 communicated with in the first step of the communication, P1 sent a message to P0 and P0 received it, and then much later in the communication, P0 communicated to P1 and P1 received it. So what we're going to try now is, we're actually going to do the sends and receives between P0 and P1 overlapped in time. So we're going to try to overlap the second half of our communication structure from the tree barrier with the first half of the communication structure. So we have communication, a send from P0 to P1 and a send from P1 to P0 happening at the same time. And they're in fact happening at the same time as a send from P2 to P3 and a send from P3 to P2 and so on. So we're successfully overlapping the second half, the lower half of our tree implementation of the barrier with the upper half of our tree implementation of the barrier. This will of course complicate the second step of the communication. You'll remember that in the case of the tree barrier, in the second step of the communication, there was some communication between P0 and P2. That will now still have to happen, but we'll talk about communication not only between P0 and P2, but also between P2 and P0, and at the same time between P1 and P3 and P3 and P1, while the other half of the processes are also doing a similar communication. And in the final step of our synchronization, P0 communicates with P4, which is what was happening in the third step of the upper half of our tree barrier. And at this point in time, when all the processes have successfully done their sends and receives, the barrier implementation has been achieved. If you can now count the number of messages that had to be sent and compare with the amount of time that it's going to take, you'll realize that this is going to be a substantial improvement over the tree barrier. Now, what would you call this barrier? If you look at the diagram that has resulted, or at least at the first half of the diagram, you'll understand why people tend to call this implementation of the barrier a butterfly barrier. These shapes look vaguely like butterflies. So in effect, we would not be too surprised if we looked at the MPI barrier implementation if we found something more complicated than the linear barrier that we first thought of, because subsequent thinking about the possible ways that the communications between different sets of processes could be overlapped gave us insight into how we could come up with a barrier that could be substantially more efficient in terms of the amount of time that it takes for the communication to be achieved. So in that sense, this was a useful exercise to better understand how the different steps of parallelizing a program may benefit from careful thought. Now, I wanted to do one more example of a parallel program, thinking about a parallel program. And this is slightly more realistic in that it's going to try to do a numerical task of a particular kind. Now, the setting is that we have an application in which it is necessary to do some kind of an iterative procedure on a two-dimensional array of floating point values. Remember that we talk about a two-dimensional array as a data structure which contains many rows of data, each of which contains many columns of data. It might be declared using, for example, if it's a large 1024 by 1024 situation with 1024 rows and 1024 columns, you can declare it in C using this kind of a declaration. If they're floating values, I might declare it as float A 1024 by 1024. Now, what the application has to do is that repeatedly, in other words, it's going to have some kind of a iterative loop. Each time through the loop, it has to find the average for each of the elements inside the array, computing the new value for that particular element of the array as the average of the value in that element with the values in its neighboring elements. And it will continue doing this iterative procedure until the difference between two iterations, as far as the values in the entire array are concerned, is not too much. And we'll quantify that by saying that the difference between the two iterations is such that the total difference of the sum of the values of the total differences between the two iterations is less than some predefined tolerance value. By what I mean by tolerance value is some predefined value. Maybe I'll set the tolerance value to 0.0001. So that is a constant. So this is a procedure which is going to happen repeatedly until the values have been averaged in such a way that they do not differ from one iteration to the next, or differ by a negligibly small value. Let's just get a better feel for what the averaging involved is. Now, if I was to try to write the C version, sequential version of code to satisfy this requirement, I might do something like this. So what am I doing? Each time through this nested for loops, I am computing the new value for one of the elements of the array. I am computing the value for a of I, comma j. Now, how is the new value of a of I of j to be computed? It is to be computed by averaging the old value with the values of its immediate neighbors. So I take the old value of a of ij, and then I compute the new value of a of ij by computing the average of the value of a of ij and its neighbors. So this is going to be the new value of a of ij, and since I know that I have to repeat this procedure until the difference between two iterations has become less than some predefined tolerance value, I compute what is the difference between the old value of a of ij, the old value of a of ij, which I had stored in the variable called temp, and the new value of a of ij. So I compute what that difference is, and I accumulate it in a running sum, and I had initialized the running sum to 0, and at the end of the iteration, I check if the total difference between this iteration and the previous iteration was less than my tolerance value, possibly 0.0001, then I know that I'm done. Otherwise, I proceed to go through this iteration once again. So this is the iterative procedure involves repeating this doubly nested loops over and over again until this condition is, the determination condition is satisfied. Now, to better understand what is going to be involved in parallelizing this activity, we need to look more carefully at what the computation step is, and this is the underlying computation step. So, let me draw a small picture which shows you Aij as well as the immediate neighborhood of A of ij. So, I am not going to show you the entire array, I am just showing you A of ij and its immediate neighborhood. So, what is the immediate neighborhood of A of ij? The immediate neighborhood of A of ij will include the previous row, but not the entire previous row, and the next row, as well as the previous column and the next column. Now, the averaging which I am going to talk about is actually going to look at the neighborhood of A of ij, which includes the element which is immediately above it, in other words the row above it but the same column, as well as the element which is immediately below it, in other words the same column but the next row, etc. So, we are talking about, in terms of the diagram, the element which is to the north, to the south, to the east and to the west of A of ij. And the way that the averaging is going to be done is to add A of ij to A of I minus 1j, add A of I plus 1j, add A of ij plus 1, add A of ij minus 1, and divide that sum by 5, and that is what would become the new value of A of ij. Repeatedly average each element with its immediate neighbors. So, I compute the sum of these 5 values divided by 5, and that is what I will store as the new value of A of ij. Okay, now you will notice that I have put the values of the different elements which are being used in computing the average in 2 different colors. I have shown A of I minus 1j in green, I have shown A of ij minus 1 also in green, but the other 3 I have shown in blue, and you may wonder why I have done that. Now, if you look at this sequential implementation of the application which satisfies our requirement, you will notice that the inner loop is stepping, I have this structure where I step through for I equal to 0, then I step through I j equal to 0, that is how I came to I j, but by the time I come to A of ij, you will notice I would already have run through this procedure for A of I minus 1j as well as for A of ij plus 1, because A of ij plus 1 is on the same row as A of ij, but on a previous column, which means it would have been the previous iteration of the for loop. Similarly, A of I minus 1j is on the previous row and would therefore have been handled in the previous iteration of the I loop. Therefore, among the values which I am adding together to compute the average, 2 are involving values which have been computed in this iteration of the outer loop, not the I loop and the j loop, but the outer loop which is repeatedly being executed until the tolerance value is satisfied, whereas the other 3 are using the old values of the array elements. You notice that each time we iterate through I equal to 0 to n and j equal to 0 through n and complete that, that is what I refer to as one iteration of the application, or one iteration at the level of deciding when we have to stop doing this thing. So, 2 of the values that I am using in the computation are using the current iteration values of the array element ij, but the remaining 3 are using the values from the previously computed or the previous iteration. Hence, I show the 2 elements which are using the current iteration values in green and the 3 values which are from the previous iteration in blue. And in talking about a parallel implementation, I will try to have the same interpretation of how to do the averaging, and that is obviously going to cause some synchronization requirements to arise as far as the parallel application is concerned. So, what we are going to look at is to look at a few decomposition options as far as how to decompose the work that has to be done across the various elements of the array, across tasks which could then be packaged into processes which could then be set up for communication, etc., etc. Now, one possible decomposition is that I could have one parallel task for each array element. Remember, there are potentially 1024 multiplied by 1024 array elements, and pictorially what this would mean is, here I am showing you the entire array A, some number of rows, some number of columns. For the moment, we are not too concerned about the number of rows and columns, except that I will refer to the number of rows and the number of columns as n. We will assume that there are n rows and n columns. So, pictorially, if I am going to have a separate task for doing the computation for each array element, then there are going to be n squared tasks, one task for each of the array elements, and this is one way to think how I am decomposing. So, pictorially, this is what the decomposition that I am thinking about, one task for each array element. Now, the first question that you will arise is, what kind of synchronization is going to be required? What is the maximum parallelism that is possible? And you will immediately realize that I could package this as n multiplied by n processes, and therefore the maximum parallelism possible, I could say, could be as much as n squared. I could have n squared processes which are at the same time progressing towards achieving the parallel task. But I do also have to worry about the kind of synchronization that will be required between the parallel processes. And if I think about parallel process, if I think about the computation which is happening for, let's say, array element ij, I realize that there is a need to synchronize with at least two of the other array elements, because it was important that in computing the value for a of ij, I used the newly computed value for the element to its north and the element to its west. Therefore, there was some synchronization that had to be done in order to achieve the same computation that we had in the case of the sequential program. I am talking about the green values that have to be used here, not the blue values, not the values from the current iteration, but the values from the previous, not the values from the previous iteration, which is what I would use for the blue values, but the values from the current iteration. Therefore, there is a need for some synchronization. The computation for a of ij should not happen until the computation for the element to its north and to its west have completed, and that synchronization must be included in the parallel program. So while the maximum parallelism might be n squared, there is going to be the need for some synchronization if I use this decomposition option. So in analyzing this decomposition option quickly, I might say that the maximum parallelism is very good. I could actually have an extremely parallel program, but there is the need for synchronization. The computation for the process ij is going to have to wait for the process to its left and top, which I was calling west and north a little while back, have completed. And therefore that synchronization is going to have to happen, and that's going to amount to a fair amount of synchronization, because that is approximately half of the, it's going to have to synchronize with two of the four other processes that it is relating to. Therefore that amounts to a fair amount of synchronization. And I have to qualify this by saying that it is a high synchronization cost. Therefore we do need to look for alternatives. Now one alternative that you could think of is to have what I call a parallel task for each anti-diagonal. And let me explain what I mean by an anti-diagonal. So once again, this is the n squared elements for which computation has to be done. What I mean by an anti-diagonal is one of the lines parallel to the line that I show over here. So this is the big anti-diagonal, and these are some other anti-diagonals. So the general idea that I'm working with now is that I'll have one parallel task for each of these anti-diagonals. In other words, I might have process P0 computing for that anti-diagonal, process P1 computing for this anti-diagonal. What do I mean by that? I mean that process P1 will do the computation for both this array element and for this array element. Process P2 will do the computation for all these three array elements, and so on. Now what is the reason behind doing this? If you think about array element ij, it is going to be computed by some particular process, say process 7. Now if I look at the diagram, I realize that the computation for this array element had to synchronize with computation for the array element to its north and the computation for the array element to its west. And in terms of anti-diagonals, both of those array elements were computed by one process. And therefore in terms of the amount of synchronization that has to be done, if I decompose the task along these lines, then the amount of synchronization that will be required for array element ij is going to involve just waiting for the computation to complete for the anti-diagonal which is before it, which is much less than the amount of synchronization that had to be done in the case of the previous decomposition. What about the extent of parallelism? In the previous decomposition, I had potentially n squared parallel tasks. In this situation, I clearly have much less than n squared parallel tasks. In fact, if the matrices were of size n by n, then the number of anti-diagonals is in fact going to be 2n minus 1, that you can confirm. And further, you could confirm that all the computations for any one of these anti-diagonals are actually independent of each other. In other words, in computing this array element, it does not have to worry about this array element at all, because the computation of this array element looks at its neighbors, which does not include this array element, and therefore the computations within any one of these anti-diagonals are independent of each other. Further, the amount of parallelism is less than the case of the first decomposition, but still reasonably significant. The amount of synchronization is much less than the previous option, and therefore this seems to be a superior decomposition to the first decomposition that we had talked about, element by element. And one could proceed to look at other decompositions. For example, you could think about a parallel task for each block of rows. What do I mean by each block of rows? This is a much simpler decomposition than the anti-diagonals. I just look at the computation of all of these array elements is happening on one process, and so on. So I have 1, 2, 3, 4, 5, 6 parallel tasks. and you notice that the amount of maximum parallelism possible is much less than 2n minus 1, or obviously than n squared, and possibly the amount of synchronization has to be evaluated. So the bottom line is that given a parallel application and moving towards given a sequential problem, a sequential version of how to solve a problem, in moving towards a parallel version of a solution to that problem, one has to potentially look at various options and analyze them and figure out which of them makes the most sense before actually thinking about writing the parallel program. And with this some brief, somewhat high-level example, I hope that you have some feel. It should be fairly clear that the second option is superior to the first, and some analysis would have to be done to place the third option into the perspective of how good it is relating to the other two options. So with this, I'd like to wrap up our discussion of parallel programming by pointing out that the activity of writing a parallel program will require a good understanding of the underlying problem and of possibly a sequential implementation of the underlying problem, but should take into account the various aspects of parallelism in terms of the overheads that might be induced by certain decisions such as decomposition before proceeding to an encoding or writing the parallel program, possibly in MPI. With this, we have finished our discussion of parallel programming, and in fact we have finished our discussion of all the topics in the syllabus of the course. I hope it was of use to you, and that it will change the way that you write your programs, make them more efficient. Thank you for participating in the course.